Hi everyone, good morning. It's exactly 11:30 and I see a few people are still joining in. So let's take a couple of minutes, a minute or two. And till then, if you have any questions from yesterday's lecture, please raise your hands. So we can take one question. So we can take one question maybe and can clarify any questions or doubts you might have had from last lecture. Okay, I don't see any raised hands here. Either everything was clear or nothing was clear. So, okay. Okay, there's a question here in chat. A class contains type of variables which contain functions, right? Like that. What does a dictionary contain? So class contains variables and functions. Yes, it has attributes, and that's how the class is defined. Dictionary has the ones in code which we had yesterday. They are called the keys for dictionary, and then for each key you will have a corresponding item. So key item pair is how you define a dictionary. So that's how that's what the definition is. I hope that is clear. The Soumyajit has a question. Yeah, please go ahead.
Yes, sir. I was just asking that if we can get the data you showed yesterday, do we have access to that kind of data from the internet so that we can just download them and plot them as graphs and animations?
Yes, that's so. It's given there, right? I mean, there is also a wget some link name given in the notebook itself. So that is the link for the data.
Yes, thank you.
That particular data is available. If you want more data like that, you can search the heliophysics event knowledge base. That has a lot of data sets if you want. Okay, so let's start. Welcome to the second lecture of Python and machine learning. Hope you got some time to go through the notebook yesterday. And today let's start with a question from yesterday actually. So there was one nice question which I said I'll go look back. I don't know if that person is online, but the question essentially was when you do a plus b and you have this plus operator and it's mapped to this function called underscore underscore add underscore underscore. How is this done? So the question essentially was, can we take any other symbol and map it to some function? And that's actually a very good question. And I had a fun time looking and reading up what it looks like. So if you are able to see my screen, this is something I found on Stack Overflow. So whenever you do any sort of coding, Stack Overflow is your Stack Exchange is your best friend. So you get everything here. So what this person says or shows is that when you have a plus sign, the interpreter, that's the translator for the code, the interpreter looks at this plus sign and calls a particular function. So the interpreter reads like line by line or column by column. So it reads these spaces, reads the R, E, P, U, R, and stuff like that. When it comes to this plus, it calls a function, and that function is called binary add. Now, binary add is a C function, and what Python internally does is it will check if the first number and the second number are integers or not. If they are integers, it will just do a normal addition. If they are strings or they are lists, it will just append these two. If it's not either of them, what it does is it calls this function called pi number underscore add. So this pi number underscore add internally it checks if this b or the first the operand a has an add function or not. So it checks if this add function is present or not and then calls it. So that's how. So it's not like you directly go from the plus to the add. The plus is interpreted as calling this function called binary add, and then from binary add you have a bunch of test cases or check cases, and if one of the check cases is satisfied, which generally is satisfied, it takes this case corresponds to a call to the add function, and that's how you do the addition. So one quick exercise for you, which you can just go home and do it, is that in that add function, just change the plus sign to a minus sign, and you'll find that the plus will now act like a minus operation. So if you do 3 plus 2, you get 1 or something. So that's a sort of a fun step with Python. I had a lot of fun going through this, but please go ahead and see how this works for advanced users. This is not for everybody. If you are feeling confused by this, then that's no problem. You don't need to know how this thing works internally. Now, one more thing is all of the codes, all of the lecture notes are being uploaded on this GitHub profile, and I have created a discussion section here. So you can click on discussions, and then you can add a new discussion here. So possibly see. So I'm not signed into this right now. There's a add new discussion option here. You can add a new discussion, put your whatever comments you want. You can click on this. You can I have asked you how your GIF making is coming through. You actually have options to keep adding responses here or put reactions here. They're like, oh yeah, thumbs up, thumbs down, and stuff like that. So this is a nice forum where all of you can participate, ask your questions, and see how it goes. And don't worry if you think your question is stupid. There are no stupid questions. There are only stupid answers which I would give. If you have a question, there is a very high chance everybody else or a lot of people have similar questions. So if you can post them here and others look at it, then even their doubts are clarified. Okay. So for today's assignment, when you click on the notebook, you click on the regression notebook. So I just close this, and this regression notebook opens up here. And then you click on Google Colab again. You'll get a Colab kernel, and you can just connect to a runtime and start using it. All right. So now we are coming back to our subject of today. And before we jump into machine learning, I'll ask you a simple question. This lady was the first person to classify stars based on their spectral characteristics. Who is this lady? I'm sending a link in chat. I hope I can send a link in chat. Yeah, I'm sending a link in chat. Please answer. This is like yesterday. You answer it within 15 seconds. Your time starts now. We'll see how many of you get it correct. I made this video using this MyHeritage website, which was getting very famous. So basically, we just have a picture of this person, but the software makes her smile and move her head. Let's see. Do we have responses? Let me do some responses. Okay. 32 to 3. Most of you are saying it's either Henrietta Swan Leavitt or it's Anijam Cannon. Okay. 40. Fine. 40 is a fine. 43. Okay. Okay. It's predominantly you're saying it's Henrietta Swan Leavitt. It's actually not Henrietta Swan Leavitt. It's Anijam Cannon. Anijam Cannon she was given the title of a Harvard computer. She would look at the spectra of various stars and see specific features and see which stars are similar, which stars are not similar. So what we do using machine learning today, where the machine automatically identifies features or there is this emission line, there is this absorption line and stuff like that. She was looking at it manually on glass plates in 1900s and classifying them. So if you get a chance, please go and read her papers. You will not be able to read them because it's like a bunch of tables all through the papers, wherein she has put up the data of what all ions are, what all spectral lines are present in each spectrum of different stars. So it's amazing what she has done, and it's Anijam Cannon. It's not Henrietta Swan Leavitt. Henrietta Swan Leavitt was the person to discover Cepheid variables, and yes, she was like a senior to Anijam Cannon, and all of them together they started this spectral analysis of stars. Okay, so that was a nice exercise. What is the menu for today? We'll do a recap of the data which we have used yesterday, because remember, data is everything in machine learning. And then obviously what is machine learning, and we look at some algorithms, not some algorithms, we just look at uh, one algorithm that's called the neural network, because the other algorithms are pretty complicated. You can't explain them without going into theory. Deep neural networks, I can give an overview, and we write some code, and finally we'll have an exercise. So the classification exercise is not present because yesterday I overshot by a long margin because I was rambling about. So the classification exercise is not present. It's just the regression exercise wherein we are going to use PyTorch for our work. What are these exercises? We'll come to it later. So first off, what did we see yesterday? We had looked at this data from the sun. This was an active region loop data. This was fixed data. So these were like bunch of images taken at different times. And then we looked at tabular data, wherein you had various features present for different objects like a galaxy or a quasar or stars and stuff like that. So this was tabular data which was saved in a CSV file. We used pandas, if you remember, for loading this data. But these are not the only kinds of data, right? Astronomy offers you a vast variety of data. One is this data which you might have already seen in the previous lectures by our experts here. This is the gravitational strain signal, and this is a time series data. So things are varying with time, and you want to look at what's happening with time. Oh, this is a new signal that's coming in time, and how does the signal vary in time? So these are time series data. That's pretty different from these other two kinds of data. And finally, we have spectral data also. So we have not looked at any spectrum of stars right now. They have only used these, UGRIZ are photometric data. That is, you consider one certain wavelength range. So let's say between these two wavelengths, consider this whole set of wavelengths, and you just put a filter there and look at the object. That's it. So that gives you whatever emission is coming from that wavelength band. It doesn't tell you how much emission is coming from this. If for lambda equal to something, what is the wavelength? What is the intensity? It doesn't tell you that. It just tells you in this wavelength range you're getting some intensity. That's all. So, but that has a lot of value because that's very fast to do. But a lot more information is present in the spectrum of various objects. And so spectral data is very important. You can infer Doppler velocity, Doppler how fast objects are going here and there. You can also infer the width of these lines that's supposed to tell you something about the velocity distribution of the thing you're looking at and stuff like that. So the spectrum of a star or any object offers a lot of information. And this spectrum that I show you here in this slide is from the magnesium line. It's supposed to be one line. Okay, and you see all of these weird features coming in. This is like a nice line. This is not a line. This is like some there are two peaks and whatnot. It's a single transition. So these things like these occur because of complicated physics that occurs at the location where the lines are forming. Sometimes they also occur as the light is coming through towards us. There's something happening in the line of sight, and you get things like this. So these are all different kinds of data. They tell you a lot more about the object you're looking at, and it's not just restricted to a bunch of images or just a tabular data. Okay, so the key word that you must remember is called the features. When I say the features, what are the features? Features are important markers or important things containing information regarding what object you are seeing. So for example, if you take a spectral line, the feature is a spectral line itself. What is the, or you could say the feature is the, if you fit a Gaussian to the line, for example, what is the peak of this Gaussian? What is the width of this Gaussian? What is the, value of continuum? Things like these things are all called features, but that need not be the very specific features. You can simply say that this whole image is like a bunch of features with these, loops coming out and whatnot. So whenever we say that we are looking at one particular column, for example here, or one particular thing in a data, we say we are looking at some feature in the data. Okay. Now, what is machine learning? This is again from Wikipedia. Machine learning is basically just a study of algorithms that can automatically improve performance through experience and by use of data. So through experience would be by specifying some scheme of improvement. And by use of data is because you can always take like one data point and do something with it. But if you keep including more data, it would generally mean that you are trying to get a better approximation for the underlying process that's going on. So as you keep getting better approximations, you keep getting better performance of your model. So machine learning will do this automatically. You don't need to sit and see, oh, is my alpha 1 or 2, is my beta 2 or 3, things like that. Whatever alpha and beta may be. The keywords here are they're computer algorithms. These are all machine learning is not like what you say in algorithm may function in a very different manner. But the common thread is that they improve the performance automatically. Of course, you can tune them. There are some pre-parameters to tune them, but the performance improvement is automatic given you have provided some scheme. And then you can, and this is primarily done by using a lot of data. Why is machine learning in vogue now? That's because of gamers. We should be thanking all these graphic all these people who are using all of these graphic cards. So we are playing Counter Strike or I don't know, GTA or something, and you need to have these all high end graphic systems. And what some people realized was these graphic systems basically do the same task multiple times in a very fast manner. And this is basically a simple operation, right? I mean, if you want to add two numbers and you have, let's say, 2 billion numbers to add, so we can just parallelize it and let 1,000 threads or something do this addition, and that is going to speed up your things very fast. So using graphic cards, graphic processing units called GPUs for computation has drastically improved the application of machine learning. We can make very complicated neural networks or very complicated algorithms. And if you have a lot of money and you can buy a really good graphic card, then nothing can beat it. I mean, you can train whatever you want. You can use how much ever data you want and train it. So that's the big reason why there is this sudden exponential rise in using machine learning since like last 5-6 years. Now we have some typical problems in ML. So I'm going to give you 3 questions, and there are some possibly right answers maybe. I want you to answer these questions, and we'll see how this ties up with what you generally mean by machine learning. So the first question is, I'm giving you this plot here. This is from the this plot corresponds to a lot of galaxies. Okay. Now I want you to tell me how many clusters are present in this plot. Okay, share the link on the chat, and you have around 15 seconds. I'll make it 20 because I've also asked you to give a justification of why you have so many clusters. So okay, so we have 11 responses. I think that was too fast. Everybody is saying okay, not everybody. Thank you. For some people are saying 2, some are saying 1. Let's see the color coding in the plot. 3 colors are there. So the one person says only 2 distinct groups are there. Other 2 points are very much scattered. That's also true. Santosh, could you mute? Okay. So we have most people saying that there are 3 clusters. Some saying there are 2 clusters, and very few saying there's 1 cluster. And mostly it's because of the different colors here. 3 colors can mean something. Yes. Only 2 distinct groups can be seen. Other points are very much scattered. So that. This is what machine learning is about. How do you objectively say? So if I don't give you these colors, can you still say that there are 3 clusters or 2 clusters there? because I'm giving you these colors, because I'm marking these, red, green, and blue sequence, you're able to find that, you're able to say that, there are 3 clusters there. So keep this in mind, that whether, you just contemplate a bit on whether you would be able to guess there are 3 clusters or not, if I had not told you there are 3 color sequences. So just remember that and hold that thought. This kind of problem, wherein you want to find how many clusters are there in your data, is called a classification problem. This is what machine learning does in a classification problem. You give it the data, and then it tries to find out how related the various data points are to each other. So it depends. If you have framed your question in such a way that those 3 colors are present, then yes, the machine learning will say, oh, there are 3 clusters. If you didn't do that, the machine learning will not know. We don't know what it would do, right? So just pull that thought and contemplate on whether you could give those 3 clusters without the color scheme or not. Second question: these are galaxies. I'm giving you these are galaxies. Okay, I'm training you now. So you are a machine now, and I'm training you now. These are galaxies. These are jets. The question is this a galaxy or a jet? Let's see. Oh, I have to share it with you, right? So sorry about that. Very good. The second thing is present. You again have 20 seconds. You can take a couple of more seconds. That's fine. This is I have framed this. I have put this image in such a way that you will get confused. But I want to see what justification you give for whatever choice you select. The 20 seconds are actually done. I can give you 10 more seconds. No, because this takes time. Okay, your extra 10 seconds are also done. We'll see what people have written. Oh my God, we have 53 responses, 54. Most people are saying it's a galaxy. Some people are saying it's a jet. It's elongation. Okay, so I need to know what this corresponds to, right? Okay. From machine's perspective, it could be either. Centaurus A is radio emitting. I didn't say it's Centaurus A or anything, right? I just give you a picture. The machine does not know what that is. Jet forms, so it's a jet. Jet has a central bulge, here it looks like a galaxy. Jets are hosted in galaxy. It's a black hole. Come on, it's a black hole. Yeah, I didn't give the machine the option of a black hole, right? Jets are coming from the galaxy. Probability is 50. Lot of options here. It's central disk is large compared to jets. So these are the kind of answers I'm looking forward to. The central disk is large when compared to jets. Correct. That's one way of just looking at it. You don't look at the physics first. The machine has not yet learned the physics, right? Machine does not know. It just knows that there's a jet means it's like 2 things coming out or 1 thing coming out. A galaxy is like some bulgy structure kind of thing. Machine just knows that. Machine does not know what galaxy it is, what are its constituents, what kind of jets these are, so stuff like that. So central disk is large is one. It's like galaxy and jet. So the basic thing is, this is as far as I understand, as far as I remember, this is a composite image of a galaxy and a jet. So these are what are called adversarial examples. So you give examples to your network, which will throw them off like, hey, what is this, right? So one reasoning was that the central bulge, the galaxy is very large, very prominently seen. So the machine would say it's a galaxy. One another, you could say this. I didn't see any answer which says that. Just through glancing. But if you look at the jets, you can actually see the bulge structure there, right? The jets are very large in these cases because these are radio jets. These are very large in these cases. You can see the central, galaxy there, here and here. But you also see the jets here. So that you can also claim that since you see the central structure and two elongated structures here, the machine would call this as a jet, right? So this is a conundrum which machine encounters, and it is something that you as astrophysicists or we as astrophysicists should solve and put the physics there. Like, okay, this is what a jet should look like. This is what a composite should look like. Things like that. This kind of a problem where I ask you whether something is a galaxy or a jet, whether something is a galaxy or a star, or something, or when I'm asking you to pick categories, whether something belongs to A or B or C. These kind of problems are called classification problems. So these are generally when you look at I don't know if you have seen these memes, but then when you want to make a meme on machine learning, what people would say is machine learning is going to destroy the world. But then there is another image of a cat wherein there is a box put up and it says dog. So this cat or dog, what is this? These kinds of questions are answered by what is called classification problem. So you pose your problem in such a way that you want to categorize the data into various classes. This is this was a trick question. This has no correct or wrong answers, by the way. This is just it depends on the justification that you give. For you, if some feature seems prominent, you say it's a galaxy, or some feature is not prominent, you say it's a jet. So the same thing happens with a machine. The way you formulate your problem, the way you process your data, certain features will be prominent, certain will not be prominent, and the machine will say, "Oh, it's a jet or it's a galaxy." So in those cases, you need to put in the physics inside, and then say, "Look at it. Look at this. You're not supposed to look at these features. You're supposed to look at only these things. You're supposed to see only this thing, not in it's the stars in the background, for example." So this is how you play with your machine. And final problem. So this is the sunspot prediction for the next solar cycle. This is for many years, and there are these three predictions which are shown in this plot. Actually, there are like some umpteen number of predictions for solar cycle. I just took this from some recent paper, and there are three options given here. So now the question to you is, which of these three do you think is most likely that is going to occur in the solar cycle? Which of these three sunspot numbers are more likely to occur? So again, I'm sending this to you in chat, and you will have around 20 seconds more. The time starts now. Let's add this here. Have a look at the cycles. 5, 4, 3, 2, 1, 0. I'll give you maybe 10 more seconds because this was too fast. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, so your 30 seconds are done, and let's look at the responses. What do you think? So red, green, or blue? Just for reference, red is at the top, then you have green, then you have blue. What do you people say? It's going to be green mostly. Some of you are saying it's going to be red. This is so confusing, right? This is the problem with Google. No? Red color corresponds to blue, green corresponds to red. Seriously. Okay, so this blue curve, most of you are saying it's going to be the green plot. The green plot is the one. The green plot is this one. Is it? Okay. So saying this is going to be the one that's going to present. Okay. Interesting. Peak is decreasing. So there was one person who says peak is decreasing. That's correct. That's correct. True. So decreasing trend. 2 times. Okay. So either is something I'm reading it wrong. So the green color is supposed to be the mean solar cycle. That's here. But it seems like most of you are saying the peak is reducing. So okay, fine. So this is a very subjective question. You ask any person and you take their opinion, and somebody else is going to bash you. This is a question that's going to land you there. So most of you are saying the green peak or the green curve is going to be the most one that you're going to observe. The green one is here, and that could be true. It's possible that it is true because these I mean, you're looking at the mean cycle, right? The mean cycle is supposed to be the black one. So the mean cycle would correspond to what the previous cycle was. But but lot of you are also saying that this peak value here is reducing as you see with time. So it's reducing here. So it could also be the blue one. It most probably it is not the red one. It seems very unlikely unless it's a sinusoidal kind of variation. And for this, if you want to answer such questions, one is you need to know the physics properly, like what's happening inside. There are like lots of models which tell you how the magnetic field is going to change and stuff like that. That is one thing. Through purely data-driven perspective, you could possibly take some data from the previous century or something and see how this stuff is varying. That's going to be a very naive answer and not a very physics-based answer. As of now, the panel, the NOAA panel, says that it's going to be a blue cycle, and that's something I think a lot of physicists in India also agree with, that the current solar cycle is going to be weak, but it remains to be seen. Like 4 or 5 years later, so it's going to also. They also say that we are 2027 or something. You're going to have this peak in the solar cycle. So 4 or 5 years later, just come and look at this presentation if you still have it, and see what did you answer. Like, did you answer it correctly or not? So this is a very subjective, kind of a question. I'm asking you what the number would be. I'm giving you some sequence of data, and I'm asking you over the next 10 or 20 years, what are the sequence of number going to be? This kind of a task is called a regression task. It's called regression because you're predicting essentially a real or a continuous valued number. In contrast to classification, where you had no bunch of boxes, it's A or B or C. Here it's like it's a continuous set of numbers. It's going to be 25, 28, 30, 44, stuff like that. So this is a regression task. It's again a very subjective question. So you can, if you're interested in this, you can just go and see what various papers say. Each paper says something very different. There is some overlap, obviously, and we'll have to wait and see which of this is correct. But just going by some data, you would say that maybe it's the blue curve that looks that looks correct to us. So those are the three problems which we have solved, and in some level at these three problems capture the essence of machine learning. In general, in machine learning, you have supervised learning and unsupervised learning. Supervised is I'm telling you, I have this input and I have this output. I want you to tell me what the input for something else or the output for something else is. So I gave you these pictures of galaxy and jets. Now I'm giving you this image. Is it a galaxy or a jet? Or I'm giving you the sunspot numbers. What is a sunspot number sometime later going to be? So this kind of thing is called supervised. This kind of a learning problem is called a supervised learning problem. The clustering problem which we had seen first, wherein I'm asking you just open it. How many clusters are there? That's supposed to be, and that's what's called an unsupervised learning problem. You're not sitting and giving a mapping between some set A and set B. You're just trying to figure out something in one set of data itself. If you take multiple levels down, supervised learning you have seen has classification and it has regression problems. Unsupervised learning not just has clustering problems which you have seen, it also have dimension reduction problems. So let's say you have a 4K by 4K image of something and you want to, or let's say it's on a satellite, okay, then you don't have bandwidth to send it. So what you would do is you would reduce it to, let's say, 2K or a 512 cross 512 image, send it to your ground station, and maybe have an algorithm which recovers this high resolution image. So this kind of a dimension reduction, but as much information as possible of the original data is captured into a data with a lesser number of dimensions. It's called dimension reduction. And there are many methods of performing dimension reductions, and we'll not be seeing dimension reduction at all in this whole series because that is like full mathematics. Okay, so supervised learning, as I said, is basically if I have data A, I am asking what the value of data B is, and if this B, whether it's a galaxy or a jet or a star or a quasar, if I'm asking you discrete classes, these are called classes again. it's going. This is don't confuse this classes here. This class here with the class in Python. These are two different things. This is what is called a class of object, or a class of things, of a bunch of stars or a bunch of galaxies or a bunch of quasars. Is it a quasar or not? Is it a galaxy or not? So this is called various classes. That's why it's called classification. And then you have this regression problem wherein you are saying, given my data A, what is this value of data B going to be? And this B is a continuous variable. Of course, you are going to have just a bunch of individual numbers. That's all. That's how life is. But inherently, that number is actually a continuous variable. You're just sampling it at various points. So, what is the redshift of this object going to be? Redshift just can't be 1 or 2, right? But redshift can be 1.1 also. There's nothing wrong with it, right? So these are called regression problems. In unsupervised learning, within the data set itself, we are trying to find some structure in the data. And if you're trying to look at similarity between different data points and they have to group them, this is called a clustering problem. And if you have a dimension reduction problem wherein you want to encode as much information as possible in some lower dimension, that's called a dimension reduction problem. And so, what is the procedure to do? To have a machine learning problem? First step: frame the right question. So you need to frame the exact question you want to answer. Like I said yesterday, you don't frame a question like "I want to quantize gravity." You don't do that. I mean, you have to frame a very specific question as to what you want to do. For example, you want to look at the redshift of objects. You have to ask, "I am given. I want to find a relation between some observation and the redshift of the object." This is a very specific statement. So once you form these specific statements, you can then go ahead and look at what techniques you want to use. But you don't just jump to techniques. The first thing you want to have is data. When you form a science question, you look at what all data is available to you, or what all data you would want to be made available to you. So you can go and do some observation. Fine, right? It's not necessary that if you don't have data, you can't do science. You can just go and propose an observation, do an observation, get the data, and do whatever you want. So once you pose the correct science question, you ask what data you want, and you get what data you want. And this data is raw. It is not. It has various artifacts like data is missing, and like with the one we saw yesterday, we had that 9999 thing, minus 9999 thing. So that means there's missing data, right? So you need to remove all of these non-physical values. You need to remove nans and stuff like that. Remove all the non-physical part, either interpolate over them or just throw them away, because that might induce some noise in your data, and vet them. This is called vetting your data. You want to remove all that is nonsense in your data and just get the the one that has the proper information. And then you do something called pre-processing. So machine learning in general, you just can't take any data and feed it in. So if you look at solar data, our images range from the value, the intensity values in the images sometimes range from 0 to 50,000 or 60,000. So this big the range of intensities, machine will not fit at all. You are doing 50,000 into some value. You're doing some operations like that. You're bound to get a lot of error. So what you do is you do some pre-processing. You maybe do a log scaling, or if your values are strings. So a machine doesn't know what a star means, right? So the machine knows what number 2 is, because 2 is to base 10. You can convert that to decimal, and you can do what you can convert to machine language. But it doesn't know what a string is, or it doesn't know what does it mean by a star. So you have to convert or encode this particular string in such a way that the machine knows that, or rather you know that the star corresponds to this something, this some number 1, let's say, and that 1 is something that's enough for the machine to understand. And then you scale your data, as I said. So you need to scale. If you have these large variations in data, you reduce the dynamic range, you do log scaling, for example, and you do such kind of operations to make sure the data looks very balanced, and you standardize the data. So standardization means you divide the data, you subtract the mean from the data and divide by standard deviation. So in general, all whatever ML theory you might go and read, all of them start off with a uniform with a Gaussian distribution or a standard normal distribution. A standard normal means your mean is 0, your sigma is 1 for any distribution you have. So if your distributions are very different from the standard normal, you will sort of encounter artifacts, and you might not know what these artifacts are. You might not be able to debug them properly. So, and then it has also been seen that you have an improvement in performance when you do this, mean subtraction, divide the standard deviation. While inference, of course, you do the inverse. So all of these are one-to-one operations. You do one-to-one operation, train the model, do the inverse operation, get your outputs. That's how you do it. And once you do that, you need to define something called training test and testing set. So always remember, whenever you do machine learning, you have a training set on which you do the training, and you have a testing set on which you do the evaluation. So think of this like exam. You are taught something in school or in class, wherein the teacher teaches you a lot of things, and this is like a training set. You are learning a bunch of different things from the teacher. But then you go to the exam and write something which has not been known to you. I mean, you don't know what questions are going to come in the exam. So you go to the exam, answer these questions, and see how well you perform. That's the testing set. So with this training set, testing set, this data, now you can, and given you have a proper science question, now you can get the correct algorithm. Get the correct algorithm, train your model, and tune the model. I mean, obviously, first time your model will not, it will just throw up some performance. You can tune your model with some various techniques, and then check the results are making sense, they are correct or not, and then you deploy your model. This training and checking requires something called error metrics. How good is your model is something that the error metric will quantify, or how bad is your model is something your error metric will quantify, and that is something you need to define yourself. And that error metric definition depends on the science question you ask. For regressions, you have different error metrics. For classification, you have different error metrics. So what do we do today? So we have a lot of time left. What we'll do today is we'll estimate the redshift of a quasars just given its photometric colors, and this we'll do using simple linear regression and a deep neural network. That's it. And this will demonstrate the power of neural network to you in the first place. And second, it will demonstrate how a workflow of a typical machine learning problem looks like. So why should this work in the first place? So I don't know if you have already been taught this, but there's something called photometric redshift. So you look at a quasar or any object in various filter bands like B, V, I, and Z, and you have these features, these spectral lines, and these features. If these features are passed through various bands, you get a different response in these various bands. So if you look at the magnitude, for example, on the top, and as this particular feature passes through all of the different wavelength bands, simply because it's redshifted. So as things get redshifted, whatever line was emitted at a frequency, we will see it to be at a lower frequency or a higher wavelength. So just based on this characteristic, if a particular feature is seen in, let's say, the V band, but it is or if it's seen in the I band, you know how much the redshift of the object is approximately. And stuff at much lower wavelengths, you will not see them because it's generally they generally ionizes hydrogen, the intergalactic or interstellar hydrogen gas. So once that is ionized, all of that is like a sort of continuum which will go away. And at some particular redshift onwards, you will see the features coming out very well. So if you don't know how this works, just take my word for it that depending on the ratio of magnitudes between different bands, you can sort of figure out what the redshift of the object is, and we can go ahead and read maybe Paddy's book, which will have more information on how this is done. So this is just a general example I took from Kaggle, and for our case, we are using SDSS data. You have these different UG, RAZ bands. Now, if your spectrum is at zero redshift, okay. If your spectrum is at zero redshift, you will see the blue curve is what your spectrum would look like, and you will have a certain response from all of your filters. But if your spectrum is redshifted, it will keep shifting towards redder and redder filters, and you'll have a very different response from your data. So if you just look at the ratio of magnitudes from these different filters, you would know that you can approximate what your redshift of the object is, right? So before we now know what the problem is. This is a regression problem. Okay, we are given the magnitude of quasars in various bands, and we want to estimate what the redshift is. Since redshift is a continuous valued number, we have a regression problem at our hand. And for regression problem, you have a bunch of different metrics which you can use for evaluation. So the first metric is called the mean square error. So it basically says that whatever model you have, it will generate some redshift, because this is basically modeling, right? You want to form a mapping between some input and output. So whatever, and you have model in between. So whatever output your model gives, that output, how different it is from the original or known target value, that is quantified by something called mean square error. This is a very typical, error function which people use. If you want your model to be good, then your mean square error should be as low as possible. Then next you have something called the mean absolute error. So this max of epsilon, whatever, is just to make sure nothing is zero. But what it says is, for some given, let's say your z is equal to 2, and you're predicting your z as 3, let's say. What is the percentage error given your your prediction is 3 and your original target known value was 2? So just so since this has no dimensions, it's much more easier to say, is it twice the is your error twice the original value, or how small is it when compared to the original value? It gives a measure of how small or how big something is. The mean square error will not give you that. Mean square will simply say, oh, it's a small or big. What do you mean by small or big? Small or big is defined by the value you're comparing it against. So 0.1 is small when you look at 1,000 plus or minus 0.1 is very small. But 0.1, but if you look at, let's say, 0.2 plus or minus 0.1 is very large. The error is very large. So you need to be careful when you say error, when you report an error, whether it's small or large. And finally, we have something called the coefficient of determination. So this is a complicated looking function, but all it says is, if your predictions and observations are all perfectly equal, your coefficient of determination will be 1. Otherwise, it will keep reducing, and it can go to some minus infinity also. So you want this to be, you want the coefficient of determination to be as close to 1 as possible, and you want these two, the first two, to be as low as possible. So these are the 3 methods on which you will do your evaluation. For first, linear regression. So for those who don't know what a linear regression is, you basically fit a line between x and y. That's it. Nothing more than that. For x is whatever your independent variable is. In our case, our x will be the magnitudes. The yi will be the known redshift. So you're taking the set of colors. That's subtraction. That's the difference between consecutive magnitudes. You take these colors. You say there is a linear relation between these colors and redshift. You fit a line and you see what it looks like. That's it. And then we have deep neural network. So this is what a typical neural network looks like. This whole thing is called a neural network. Each ball here is called a neuron. Each vertical column is called a layer. So remember these. This whole thing is a neural network. Each ball is a neuron. Each column is called a layer. The first layer, where you feed in the data, is called the input layer. And the last layer, from where you get the outputs or the predictions, is called the output layer. And whatever goes in middle, so you don't need to have just one layer here. You can have one layer, you can have another layer, third layer, fourth layer, so on and so forth. Each of these is called a hidden layer. It's hidden because the data cannot see it directly. There's no direct mapping to that hidden layer. It doesn't go there directly. All right. So your inputs will go here. So basically, what you say is, you say this node is, or this neuron is equal to some color value 1. This neuron is equal to some color value 2, and you do a set of operations, and then you get an output here. That output is the redshift value that's going to be the prediction. Consider this neuron here, and let's label this as J. All right. So the output from this neuron, okay, once this set of presentation is over, I can take questions. So you take this neuron J, the output from this neuron J is basically, you take the inputs that are coming from from the previous layer to this neuron J, multiply them with some weight. So this first green ball is called Xi, then this edge is called Wij. Okay, so you multiply Wij with this input Xi, and you keep it here. And let's say this is some I2, let's say. So you have Wi2j, multiply that with this, neuron here. Somebody is not fit. Please mute yourself. Okay. So to take this neuron here, take the value of neuron here, multiply this with the edge value wi to j, and keep it here. You do it for all the inputs that come from the previous layer to this neuron j, and that is the summation over I, where I is basically the neuron of the previous layer. You have a w times the neuron of the previous layer. You keep adding them. You keep do this multiplication, add them all, and add some term called bias. So what this is basically is there's a matrix multiplication. So if you see this, if you remember Einstein summation, this is basically matrix multiplication. It's w dot x if you want to think about it. So you do a matrix multiplication between this w matrix and x matrix. X is the input from the previous layer, and then add a vector called bj. B's are called the bias terms. The w is called the weight terms. So here you multiply the inputs with the weights, add the bias term, and then you pass it through something called an activation function. The activation function is some non-linear function like let's say tan h. If you remember what tan h is, it goes from minus 1 to 1 at minus infinity, and it's almost linear near x is equal to 0. So you take a non-linear function like tan h, and you throw this input, the computation that you get from here to the tan h, and that thing is what is known as the output yj. That's this operation. This is a very specific operation, right? One multiplication or n multiplications, one addition, and one activation function evaluation. These set of operations generates one output from neural network. You do that for all the neurons in this hidden layer. So you have J1, J2, J3, J4, so on and so forth. So again, Yj is the output from neuron J. Xi is the input from neuron I to neuron J. Wij is the weight value of this H. Bj is the bias value of this neuron J. And F is the activation function. The W's and B's are not fixed. The W's and B's are the parameters that will be trained to generate a very good prediction. For the most optimal prediction, you'll have some set of W's and B's that will give this optimal prediction, and your task will be to find what those values are. Right? Now, it doesn't stop there, right? So from J, you can go to K. So what happens at K is, again, you have Wjk, where J, or we just take care of the notation. I think I've swapped it. So J is the previous neuron. You take the value from the previous neuron, multiply with this weight, and place it here. And do that for all the previous layer neurons. Add them up, add the bias term, and again pass an activation function. So this F and this F need not be the same. They can be different also. There's no hard and fast rule there. And this will give you the output from this particular neuron. And this keeps going ahead. From first layer to the nth layer, you keep doing these operations and you see what the output is. And the way you train is that you define an error function. You say that I have a particular okay, fine. Let's go step by step. You first initialize W and B for all layers. So you have some non-zero values. These are random values, right? I mean, they can be anything. Just make them reasonable, not like too large. And you do the output calculation of matrix multiplication, the yi's and yk's. Calculate them from the neural network, and you get a z prediction, which is basically a function of the function of blah blah blah. It keeps going like this. So this will be like this whole nested set of function. Get the z prediction. Now, the first time you do this z prediction will not match the z node because you're keeping some random values for w and b, and there will be some error between z prediction and z node. So your task now is to find those values of w's and b's which will make this error minimum. What does that mean? If you remember calculus, you will get a minimum of a function where your gradient, where your first derivative goes to 0, and your second derivative is positive. And that's something what is being used here. You take the error value for a given input and for the corresponding prediction. You update the weights using this formula here. So what this says is, for whatever loss you are getting, you take a derivative of the loss with respect to this W, and when if and when your loss has reached the minima, let's say, this term will be zero because you have found the best weights which can make your error minimum. If that's the case, your loss will not change the weight at all at this global minimum. But it's not at a global minimum; it's at some value here. So you'll have some derivative value, and what you say is, so I have some derivative value. I want to go in the opposite direction of this derivative towards the minimum, because derivative is sort of giving you an increase or a decrease, the path of increase or decrease. So I want to go in the opposite direction because that's where the loss minimum is. So your weights are being updated as W goes to W minus this derivative term. The big impact of GPU was this computation of this loss term. You can do this differentiation using chain rule from go from the loss to the WIs, and you can just parallelize this and make it very fast. This alpha here is what's called the learning rate. It's how fast the network will learn. If you put alpha to be too large, then this will not go down smoothly like this. The weights will keep changing drastically, and you will not reach a global minimum. If your alpha is too low, you'll just keep going really slowly, and you'll be just stuck in some local minimum. And remember, you don't always, if you consider the variation of loss with respect to some weight, you don't always have global minimum. You will always have some local minima where here and there the loss is not changing, but the loss is actually very large. It's not very small. So this is basically how a neural network works. You learn from the mistakes you make by changing your behavior accordingly. If you touch a hot object, right, your hands will get burnt. Now, next time you see a hot object, you will not touch it because your hands have gotten burnt. You should do the opposite of what you did the last time. Last time you touched it and you got burnt. So this time you don't touch it, you will not get burnt. This is basically the same principle. So this is how neural network training generally takes place. And don't worry, you don't need to do this formulation and all. It's all taken care of by PyTorch or any other code that you use, right? So, and you repeat this procedure till you get convergence. And why do you need data? Because if you have a lot of data, you have a better estimate for what these derivatives are for the whole data set. So then that makes your convergence better. So we'll move on to the Jupyter next. But before that, if you have some questions, we can take some questions. So I'm sorry, this is going to extend to some time like yesterday. I would appreciate if you stay here and finish the Jupyter notebook. Otherwise, this thing will be really confusing to you. So if you have any questions, you can post it in chat. Or if you have really urgent questions, you can just raise your hands. I will unmute you. Jyotirmay, please go ahead.
Good afternoon, sir.
Yeah.
My question is related to matplot, libplot. Can I ask?
So I would appreciate if you put that in the discussion section and later. If it's something related to this, machine learning stuff, then that will be, continuous. So if it's related to matplotlib, put it in the GitHub discussion. Then we can take it up there. Is it fine? Or we can take it at the end of the lecture. Okay. Okay. Yes, so I'm checking the chat. So if you, people in chat, if you can hold your questions for the previous lecture, please ask them at the end of the lecture. Okay. What do you mean by bias variable or term? Bias just is giving you a shift. So if you remember, if you know your Fourier transform and all, any constant offset is called a bias. That's the same description here. How do I calculate loss? The formula is given to you. You just feed in the it's as simple as that. How do you speed up the collab worksheet execution? I have given you GPUs for the free GPU kernel for execution. It will be slow. It will take an hour or so because there's a lot of data. If you have GPUs or if you have multi-core system, then you can use it. One question is, how is training a neural network different from numerical analysis? That's a good question. So numerical analysis, basically, I mean, if you have any model and you have any physical model and you want to match the predictions of physical model to some observation, generally the way you would do is you do a Monte Carlo simulation. You keep playing with these various free parameters randomly or in some specified fashion, and you find what the best set of parameters are for the given observation. Machine learning is something similar, but you don't play around with these parameters. You specify the loss function, you give the data, the model should figure it out, what the optimum set of parameters are. So there is a very fine line there, difference between numerical analysis, if I understand correctly, and machine learning, but it's in the same continuum. There's no very big difference. How is AI different from machine learning? AI is just the way you get funds for machine learning. So, okay, so let's move on to the Jupyter notebook. So today I will not be running this notebook because this takes, as some of you might have seen, it takes around 1.5 hours or so to run the notebook. See, it says no connection lost, but that's okay. So I just show how this is done. So first step is loading our packages. Okay. So we have framed a science question, right? I mean, if you remember the science question, we have photometric data. We have the magnitudes. We need to map these magnitudes to the redshift, spectroscopic redshift that's already given to us by SDSS. Why would we want to do that? So one thing is spectroscopy takes a lot of time. Okay. And if for a survey like SDSS, where you're doing observations every night, you're generating spectra of, you're generating data for hundreds of thousands of objects in total. Going and sitting and classifying or looking at the redshift of each star or each object, redshift of each galaxy or quasar is going to take a lot of time. So if we can have a model or a machine learning model which generates this mapping between colors that you obtain from the SDSS and the photometric and the spectroscopic redshift, then that can serve as a proxy for what the actual redshift is. Obviously, it will not be the same. We'll always have some errors, and as we see, we have some errors. But this can, at some level, automate the generation of redshift. And then, when the researcher is interested in a particular object, they can just go ahead and request for the spectrum of that object and figure out how different the redshifts are. This is why we need to do a job like this. And by the way, SDSS already uses machine learning for doing this task. So it's not something you're doing too. They're just doing it at a much larger scale, and we don't have compute to do that. So the procedure here is we first need to prepare the data. We have seen those negative values yesterday, right? So we need to prepare the data, we need to process it, and we need to do the pre-processing with the standardization and whatnot. And then we look at the linear regression with 3 squares, and then we look at the neural network with PyTorch. So first step, you load all your data, you load all your packages. So NumPy, for any manipulation you want to do, you use NumPy. Matplotlib for plotting. Pandas, because we want to read the data frame in. The data frame yesterday, or the CSV file yesterday, the table that we had was read in using Pandas. So we are using that. And this warnings and filter warnings is something I generally input, because sometimes you keep getting these random cryptic warnings which have no use whatsoever. So to ignore them, I just import warnings. I say, ignore all these warnings. I know what I'm doing. But don't do that. I mean, this is something I'm just doing it because I don't want to see these warnings pop up everywhere. So, okay. This line is not required actually. GDown is already installed in Colab. And then somebody was asking me where we get the data from. So this SDSS data, I have given it to you in a Google Drive link, and this is the ID for the Google Drive link. If you just run this cell, the Google Drive link will be downloaded. So let's see. The data is not here because the kernel reconnected. So I need to reinstall. I need to download the data again, and this will download to this particular location. And this is not a lot of data, so you can download. So it's like a couple of seconds, done. And this is to upgrade scikit-learn. For some reason, the Colab was not having the latest version of scikit-learn, so I just upgraded that. That's not required. Just forget it. The main code starts here. Load the data into a variable called data, and you investigate what the data is. This is what we had yesterday, right? We had this bunch of various rows, a lot of columns with UGRIZ. That's what we want. We had the class of the object, that's galaxy, quasar, or a star. and then you have the redshift. These are the important columns for us. Remaining everything is not required for us right now. And we know from yesterday that some of the data had this minus 99 in value. So you just remove those rows altogether. We don't need them. We have a lot of data, so we don't need these rows. Remove them, and you have this data which is processed, which is pre-processed and ready. Next, we have the first step. That is, you have to convert these magnitudes to colors. So magnitudes basically is like flux. It is luminosity per squared distance between the object and us. So something might look dim simply because it's far away, and we don't want this. We don't want the machine to capture this dimming directly. What we want is, given I have some intensity in or some flux in M band or in G band, how much more flux is present in the R band or I band. That is what I am interested in, because as a feature, as a feature of importance in quasar passes through various bands, the relative magnitudes is what is changing. So you take the class and redshift from the data, and you make a new variable, you make a new data frame called df, and then you keep adding new columns. The first column u underscore g is basically u minus g, the magnitude in u minus magnitude in g. If you subtract magnitudes, remember you're taking the ratio of fluxes. This basically means the ratio of flux in u band to g band. So your L by 4 pi d square. So that the d square 4 pi d square gets cancelled off in both of these numerator and denominator. And all you are left with is the luminosity in u band by the luminosity in g band. So this is more like is removing the artifacts due to the distance. And then I did this exercise with considering galaxies and quasars, but the model took like 5 hours to train, so I'm not doing it now. I'm just taking the quasars and seeing if I can estimate the redshift of quasars or not. That's it. It's a much more simpler task. You just see what this data frame looks like. You have a class, you have redshift, and you have the colors, which is the difference in magnitudes. And first off, drop the class. We don't need it. We needed the class because we wanted to get the quasars rather than the galaxies and stars. But now we don't need it. We know everything is a quasar. Just drop the class. It's not changing at all. So the columns we have now is redshift and the colors. Okay. And now you take the raw values. So this is a data frame, right? If you want the values in the data frame, you select these columns and do a dot values. So this input raw is a raw value. Is the color value as present in the data itself, and the output raw is the redshift value as is present in the data itself. And you have like 54,000 data points for quasar. Yeah? Or let's say you have 54,000 quasars in your whole setup. So there is a question, it seems. Yeah, Sachin, please go ahead.
Yeah, thank you. You just shown us the definition where you are like defining a G something. Just scroll it up.
This one?
Where you are defining the data. Yeah. Yes, yeah. So why you have used that underscore over here while defining the not space? Underscore. Yeah.
It's always a bad practice to have space in names when you're doing Python. Okay, so it's just a notation. You can just say UG if you want. The way it's nothing. It's just some fancy way of writing it.
Okay, I can use like UG directly, right? Without giving underscore. Yeah.
You can use whatever. So it's up to you, right? You can just write the whole thing. Color in U band minus G band. You can just write the whole thing as a text. There's nothing wrong with it.
Yeah, I was confused in that. But thank you.
Okay, so if that clear, let's move ahead. The output generally in any machine learning problem, you have it as the number of objects you want as the number of rows, and the number of features as the number of columns. This is a norm. Always the number of rows will be like one observation. So first row is one observation, second row is another observation, so on and so forth. And the number of columns will be what observation are you doing. So first column is so in this case, in the output raw, there's only one column, and that's the redshift. In input raw, we have multiple columns. The first column is the UG color. second is GR color, and so on and so forth. So just to make sure, we'll just see what the distribution looks like. This is the distribution of redshift. You can see predominantly there is a lot of redshift near 1.5 or so. And then there are a couple of outlier redshifts at 4, 5, 6, and 7. Very few values are there. And this is the U minus G color. And this near is 0 somewhere, it goes till 1 or 2. That's it. So this looks like a typical distribution that you generally have. Now, what you do is, I told you that you should, it's a good practice to scale your data by removing the mean and subtracting by dividing the standard deviation. So this process, you do it for every column. So if you take the U minus G color, let's say, for all the observations, you subtract the mean in that column and divide by the standard deviation of that column. You do this for all the columns to make sure all of them are at an equal footing. So sometimes you might have data wherein one is like 1000 to 2000 and the other is 0 to 1. So you can't, if you simply feed it to a machine or to any algorithm, it will say, oh, 1000 is bigger than 1, 1000 is more important. But that is not the case, right? It's how much it's varying that's more important. So the standard procedure is to remove the mean and subtract the mean and divide by standard deviation per column. And Python offers us packages to do this. So okay, if you see this message, I'm getting a message called you are connected to a GPU runtime but not utilizing GPU. So you have a GPU runtime, and you can check that by going to runtime, manage sessions, and then you can select GPU or change runtime time, and you can select a hardware accelerator called GPU. That's how you use GPUs in Colab. So anyway, coming back, I define a scalar for X, a scalar for Y, and modify the input columns in such a way that all of them are standardized. That is mean removed and divided by standard deviation. So this mod, if I'm giving a mod, input mod, output mod, it is modified or standardized data. Next step is to do the training testing split. So this is basically a fancy way of saying randomly I will assign 85% to training set and 15% to testing set. So that's saying, I'm going to teach you 85% of the stuff in class. 15% of the stuff will come in exam, which is based on what I'm teaching in class, but not the same thing. So this is how you set papers in exam, if I'm not wrong. So this is what we are doing here. We're just shuffling indices and generating a training set and a testing set. The training will take place on training set and the testing on the testing set. It's as simple as that. Now I'm just creating the training and testing, original values, whatever they are, by an inverse transform. So this is how simple it is. If you want to standardize, you do a transform. If you want to not unstandardize, like put back the mean and standard deviation, you do an inverse transform. That's it. And then I'm generating a couple of simple functions to make sure I'm able to get my results out properly. So for example, this is the mean square between target and prediction. This is the mean absolute percentage error. This is the R2 score. So all of this is defined in scikit-learn. SKLearn is scikit-learn, by the way. And all of this is defined. So if I just call this performance with a target and prediction, it will give me the summary. And then I have a function to make the scatter plot because I'm too lazy to copy paste this code everywhere. Just makes a scatter plot of target and prediction. That's it. So with that out of the way, first let's do linear regression. Linear regression, as we know, is basically just fits a line between the colors and the redshift. It's just fitting a line with some. So y equal to mx plus c. That's the general formation of line. But since x is 4-dimensional or here, it's a matrix multiplication plus a vector. And it's not very complicated. You just input this package, linear regression here, and you do a fit between x train and y train. You can check what the coefficients are, you can check what the intercepts are, and then you do a predict on the x train and y on the x train and x test, which are the training and the testing set. So you just like a couple of lines of code, then that's it. You have a simple linear regression model with you, and you have the predictions from the linear regression model. But these predictions, if you're still following this, these predictions are not. These are standardized. These are the standardized scale. So you do an inverse transformation, and you get the predicted predictions which are unstandardized. And then what you can do is get the statistics of how good your model is. So for this linear model, the mean square error is some value, which I can't make sense of anyway. The absolute percentage error is 1.6. The R2 is 0.11. This is for training set. 0.11 is horrible in the training set performance. Testing set is 0.13, and that's simply because we have like 15% of data only in testing set. That's it. And so basically, it says that a linear model cannot fit between the color and the redshift values. This is what you infer from these statistics. Because your R2 score is low, your percentage absolute error is pretty large, and means for error is large. And if you just make a scatter, this makes sense. Your targets are on x-axis, your predictions are on y-axis. You want a straight line between these two, to get a proper prediction. But that's not what you are saying. You are just getting a straight line which is like horizontal, which means it's not training at all. There's no training happening here. It's a fitting, but that fitting is useless because it's a linear model. So a linear model will not fit the color to the redshift. But will machine learning model do that? Will a deep learning model do that? Let's look at PyTorch and see if this actually works or not. So if you are already doing machine learning, you might like to use TensorFlow or Keras, which was what I was using for a long time now. But a lot of people are using PyTorch, and I have codes ready in PyTorch, so I'm using PyTorch too. But whatever I say generally holds for all machine learning models. So in PyTorch, there are three basic parts. First part is a model class. Second part is a data class, and third part is a training iteration. So you define your model somewhere. You define how you load the data, how you process the data, and all somewhere. And then in the training iteration, you take in the data, give it to the model, train it. And then, so this is a bit more lower level. You take the data, give it to the model, and get to the predictions out first. And then you say, oh, I have the predictions, I have the target. What is the error? Find the error, and then you say, this is the error, this is the model. Now use this error to train your model in this iteration step. So you change your weights in one go. And then you keep doing this process again and again until you fix some convergence limit or some number of iterations. If you didn't understand this, don't worry. We'll come to it now. So first off, we import the packages. It's called PyTorch because it's the Python library for Torch. Torch was written in some language called Lua. It's a very old package. So you input Torch, and Torch NN is Torch neural network, and Torch riddles is the one that contains the data class. So the model class uses NN, the data class uses data. All right. And next, I have defined a small function. So before we go to these functions, you must remember one thing. We were using all these variables, right? Using NumPy, matplotlib, and whatnot. So NumPy variables are all called, NumPy arrays or NumPy objects. So these are all like objects of a class which is present in NumPy. Similarly, Torch uses objects or stuff which are present in the Torch file, torch.py file, if you want to think about it. And these are called Torch tensors. A Torch tensor is different from a NumPy array. These are two different things. The difference between them is something like there's a difference between a number and a string, right? These belong to two different categories of objects. So it's something similar also occurs here. A NumPy array is different from a Torch tensor, but you can convert from one to the other. So you given a NumPy array, you can convert that to what is called a Torch tensor, and this Torch tensor is generally present in your CPU. It's in the CPU memory. When you are training on a GPU, what you generally do is you take this variable and place it in the GPU. The GPU is like a different, it's something you attach, right? So it's a different, a card or something that comes in the system. So you take this variable, place it in GPU, do your computation, take it from GPU, place it back in CPU, and still it's still a Torch tensor. If you want to do NumPy operations, you convert this Torch tensor to a NumPy array and do whatever you want. So it's a very roundabout procedure. So you have a NumPy array, convert that to Torch tensor, and if it's in GPU, if it's in CPU, you take it from CPU, put it in GPU, and if you want to do some inference on the NumPy array, you go all the way back. And to do this, conversion from NumPy to Torch tensor, I have defined a function called float, which takes this, which takes this NumPy array for tensor and converts that to a Torch tensor. That's it, nothing more than that. And now comes the model class. The model class, we have seen this inheritance in the previous lecture, where the re-DNN or the redshift DNN, as I call it, is basically inheriting from this neural network module, and this defines a neural network. what this says, forget about everything else. Just look at the shaded part. What this says is I have some number of inputs called n in, which is the number of the number of neurons in the input layer, and then I have 12 layers, the 12 neurons in the next layer, then 26 neurons, then 14 neurons, then 7, and then I have n out, that is 1. So in our whole problem formulation, I have 4 inputs, then I have 12 neurons, then 26 neurons, then 14, then 7, then 1. That's the number of redshifts. And this is the way the forward pass, as I say, is done. Give the input here, you get the output here. And the forward function does this. It takes in the input by colors, it passes through this whole neural network and generates an output which has just one value. This NN sequential is just a fancy way of writing a neural network. That's it. Sequentially, you are throwing an input from here, getting output here from the bottom. The LU is called exponential linear unit. It's an activation function. You can just read up what it is. It is just a non-linear function. That's it. Nothing more than that. It ensures that you're not just doing a bunch of matrix multiplications. That's not required, right? If you have 2 matrix multiplications, you can just take the third matrix, which is just a product of these 2 matrices. But you don't want that. You want something non-linear. So you have these non-linear activations interspersed between these multiplications. So this is how you define a machine or a model class. Then you define the loss function. So I have the mean square error as a loss function, and then this is present in the this mean. Okay, so this is what you do as a mean square. So this is the squared value. You take the mean of the value, and then detach CPU numpy. Basically says that you are taking this value that was computed in the GPU. You are taking it up, putting it in CPU, and now it's a torch tensor. But we convert this torch tensor to a numpy array, and you put it to numpy. And so so then you can do whatever you want with numpy. You can plot it and do all sorts of stuff you want. And then this graph performance is just a performance. It just generates the performance statistics by taking the values from the GPU and giving it to numpy array. And loss function, as you see here, is just a mean square error. Nothing more than that. Always remember to set the seed of your random number generator whenever you do any computation. And this next line just gives you what device you want to use. Do you want to use CPU or do you want to use GPU? GPU is used by CUDA. And then you have the data class. The data class tells you that the data class basically takes in the data set and gives you values for given indices. So for example, it takes in features, target, and generates a number of outputs and input. And what it does basically is, if I want the first element in the data set, then it will give the first element in the data set. So I've got features of index. So A of 1, A of 2, that we had seen yesterday, that A of 2, that thing is interpreted as calling the get item function in that given class. This is very similar to how the plus sign becomes the underscore add underscore. In the same way, A of 2 in square brackets of 2 gets interpreted as get item where the index is equal to 2. So you just take the second index, second variable of the data set. And now I have some basic parameters called batch size. LR is the learning rate. It's how fast or how slow you learn. And I train this for 9,000 iterations, 9,000 epochs. Batch sizes at a given time, how many data points do you fit? Do you fit the whole data set at a given time, or do you fit in blocks of data? That's it. So this whole cell basically defines the data class. This training loader and testing loader are what are going to generate these individual samples, and from these samples you will be training your neural network, and then you define the network. So redshift model is an object of this class, which has 4 inputs and 1 output, and then you take this model and you save it in the GPU, because that's where the training and all is going to be done. And this is what the model looks like. You have four inputs, and you have 1 output, and then you have all of these layers in between. And then the way you are training. So I showed you that then W goes to W minus alpha times some derivative of loss. There are multiple ways of doing the same thing. One such way of doing it is called Adam. It's an optimizer, and you just I'm just using NM optimizer because it's very peaceful to use. If you want to know more about it, just go and read it up what it is. And this is just for the performance statistics. And finally, given all of this stuff, we can go and train a network. So what I do is for each iteration, for each of the 9,000 iterations, I take all the data in the training set, and I say, first of all, this is the first pass. So all of my gradients are 0. I am going to take this data, give it to the model, and generate a prediction. That's the predictions here. Now I have the predictions and the target. Given these two, I'm going to know what the loss is. The first time loss will be very, very large, very bad. But as time goes on, the loss will become smaller. So you get the loss value out. And then you say, okay, this is my loss. These are my weights that I'm getting from this redshift model. I want you to take this loss and update all the weights and biases in this redshift model. And that's what is called the loss dot backwards. It computes this loss. And optimizer.step actually does the computation and updates the weights. So it's done in 2 steps. It's done multiple steps. You take the data, you generate the prediction from a given model, you compare the prediction to the observation and see what the loss is. And then you say, I have this loss, I have this model, I want to find the derivative of the loss with respect to all the weights and biases in this model. You compute this derivative and keep it somewhere. And then you say, okay, I have these derivatives, I have these weights, I want you to update these weights given these derivatives. You update them. You keep doing this for the training set. Testing set, you just find what the loss is and just note the statistics. You don't train on the testing set. You don't take your exam papers, right? The same way you don't train on the testing set also. So you keep training this. So this thing has taken around more than an hour to train, and this is what you get. So all of this is in log scale. Initially, you had some very large error, and this error drastically comes down and keeps decreasing and has saturated at some point of time. So this means that your model has started to converge. It could converge to something garbage. That's perfectly present. But in this case, you'll see it's not garbage. It's some proper prediction. So with this model converged, now you can put in all of the data that you have and generate predictions out. So you generate all the predictions. There's the predictions from this model, from this neural network model. You do the inverse feeding transformation, the standardization transformation we did initially, and generate what the statistics are. For this neural network, you see that the mean square error is much lower. It's 0.18 here. The percentage error is also lower. And the R2 score is pretty good. It's 0.63. It's not 1, it's 0.63. And we'll see why that is in a moment. Our training set and testing sets have very similar statistics, and we see the percentage error is larger, obviously, in the testing set. But the R2 score is pretty good in the testing set also, which means that the model has learned a lot of association between the color and the redshift. And this association is not linear, it's very non-linear. And that's why the linear model fails, neural networks are working. And if you just do a scatter plot, you'll see that the scatter is good till 2. So till 2, there's almost like a straight line. But then this stuff here is not printed well at all. This is all like some garbage for the neural network. It's just throwing out some values. And why is that happening? Because you have less samples there. If you remember the distribution of our data set here, where that is here, you see that most of the targets are less than 3. There are only few samples that more than 3. So our model doesn't predict as well at redshifts more than 3, and that is why you get bad performance here. So if you account for that and do some gimmicks and do some jugaad, you will be able to get a better performance in your neural network. So this is how the workflow of a neural network looks like, basically. Now, I have gone way over time, but I can take questions. So if you have questions, please raise your hands. I think I'll take those questions first, and then I'll go for the chat. So any questions? Let's start with questions in this, this notebook first, in machine learning first. If you didn't understand anything at all, then that's fine. I can answer them. So let's start with these questions first, and then we can take questions from the previous lecture also. You raise your hands and I'll unmute you. Yeah, Jyotirmay, please go ahead.
So the earlier question I'm asking now.
Okay, fine.
Okay, means using matplotlib module,
Hmm.
We have did one experiment on the radio wave experiment.
Okay.
And we kept some reflector on the back side of the source, and we are taking the receiving signal from the front side by by changing the distance between the reflector and the source. So
Okay.
we get some data, but it could be sinusoidal. But when I am plotting with this matplotlib, it is not sinusoidal. So means how to make it how to fit I with sinusoidal means by creating more data by interpolation, and how to I fit it with sinusoidal curve.
That's a very specific problem. I don't know. I need to see the data first, what it is, what it looks like, and only then possibly I can comment on it.
Can I share my screen?
No, I mean, if you have these questions, so is this was it a part of the summer school, or is this something you're doing by yourself?
Yes, it is part of the refresher course.
Oh, I see. So this was taught by Neeraj, I guess.
We have they told us to do carry out this experiment.
Okay.
We carried the experiment. We got the data. When I'm plotting with matplotlib, it is sinusoidal but not smoothing curve.
If it's not smooth, that's because you don't have enough samples between 2 points. So you could do an interpolation if you want. I mean, you can just check SciPy. SciPy is a scientific Python package for interpolation. You can check that. Or even in plotting itself, you have some interpolation options in matplotlib. So you could check that. Possibly that will mitigate your issues. Does that make sense?
No, means I don't know how to do that.
Okay, fine. So since this is not related to exactly what we are doing, we'll take it up later on if possible, or go to GitHub and post this thing in a discussion there, and then I can look at it in leisure and see what it is. You can just put the plot and you can just take a screenshot of the data that what it looks like in the GitHub discussion section, and then we can discuss that.
Everything I have now.
We need to. So let's come back to this course and let's if you have specific questions and what is going on since last 2 days, let's take those first, and then we can take these general questions in the GitHub discussion section. All right?
Okay, thank you.
Okay. Okay, any more questions? Chat. I'm checking chat now. Okay, somebody is asking me to take 4 more sessions. I get it. I mean, I understand. This is a very intensive, thing. 2 lectures are not enough. Believe me, I gave like 3 lectures to a couple of friends of mine, and even that was not enough. And that was only neural networks, nothing more than that. Just deep neural networks with the maths part. So this is a very difficult topic. The point of this thing is not like you become expert in what neural networks are or what machine learning is. The point is that you have a starting point for understanding what the workflow looks like. What does it mean by a loss function. Even if you just remember those 3 exercises we did today, that is a really good take home message for you. So so don't think that you'll be an expert in this or something like that. So it's very difficult. You have to go back and do a lot of reading by yourself. So there is another question. I'm asking you to unmute. Rafi, please go ahead.
Yes, am I audible?
Yes, you're audible.
Yeah, so my question is, so how does the machine learning system and everything relates to Bayesian statistics? Can you explain on that?
Okay.
Yes.
Okay, that's a good question. Machine learning is at some level based on Bayesian statistics. The optimization scheme. First of all, why do you need means per error? Why do we always use means per error in whatever task we do? That is because if you look at a simple Bayesian formulation of a fitting problem, and if you consider I think I can show the slide itself. So let us see. Okay. So look at this expression here. this target y is equal to b0 plus b1x, or that is your model, plus this error term. So basically what it means is y minus y0 or some y prediction is equal to the error term. Now consider if your errors are normally distributed, they follow a Gaussian distribution, then and if you want to minimize this error term here, it would mean that y minus this y prediction whole square, that's how you get a Gaussian, that should be as low as possible. So from there you get the means per error as a formulation. So you can actually Google it up. It's a very nice way of saying if your errors are normally distributed, your error metric in general, if you want to maximize your likelihood, so that's the correct term. If you want to maximize your likelihood, and if your errors are normally distributed, then your target function that you want to minimize will be a mean square error. So this is one way in which Bayesian statistics relates to machine learning. This is not the only way. All of your variables are normally distributed. Basically, you have a posterior or you have a likelihood that you want to optimize. Your prior, when you keep saying Bayesian statistics, you keep saying, I am setting a prior over my variables. The prior over your variables is basically this first line here. Initialize W and B for all layers. That's setting your prior in your data, in your machine. And this calculating this output in this error function. That is basically calculating the likelihood in some sense. And optimizing for the maximum likelihood estimate is obtained by this gradient descent, as this technique is called. So that's how the whole machine learning relates to statistics and Bayesian statistics. So is that clear?
Yeah. Thank you so much.
Okay. Yeah. Okay. So the chat. Can you please suggest some reading material for machine learning part? Yes. So when I share the slides on GitHub, you'll find many references there, many lecture notes there of various experts in the field. So you can just go and read them and see what it looks like. So one thing is machine learning. I mean, this is my opinion that machine learning needs a lot of theory work from your side. So even if you do, PyTorch.fit or something, or sklearn.fit or something, you need to go back and read what the theory is. Only then will you understand in some depth what I'm saying. But this is supposed to give you an outline. Right. So that's what a lot of people have asked me. Do you have any specific questions in this lecture? Anything that you didn't understand? If you didn't understand anything, also that's fine. I mean, give me some specific step or something, I can explain that. And meanwhile, I can look at the chat, what's going on here. So there is one question asked by Arpita. Is the regression part used to explain the procedure of verification of a certain classification? What does that mean? I'm unable to understand the question. If you could raise your hands, I can unmute you. So Arpita Saha has this question. This was asked an hour ago, so I don't know if they are there online or not. But if you're there online, if you want to clarify what this question is, then I can answer it. So there was one question on the green plot shows no red regions. I just took the plot from some random web page. So don't go too deep into that. It was just a scheme for you to understand what classification means. So if you think about this error region. There's no error region anywhere. What does that mean? So this thing, if you know what this plot is, this plot basically is that you have elliptical galaxies and spiral galaxies, or the old galaxies with a lot of old stars and new stars. So that's what this plot is supposed to represent. The red sequence corresponds to all of those galaxies with old stars. The blue one with all those galaxies with new stars, or these are star forming galaxies or something like that. So that's what that plot means. There's one question by Aisha. Does classification problem depend on significance value? Significance value of what? Could you clarify, Aisha? Maybe you can raise your hands and I can unmute you.
Hello, sir. Am I audible?
Yeah, you're audible. Please go ahead.
Sir, when we do the classification, especially in case of clustering, we k-means or something like that. So, do we have significance? Like, say, for example, in statistics, if the any value in case of chi-square, minimized chi-square value, if the significance is less than 0.05, then the classification, whatever we have got, is we are sure about the classification around 95.9% or something.
Right.
So my question was related to that. Can you please clarify?
Right. So in clustering, what generally happens is what is the basis of clustering? Clustering. So most of the clustering algorithms, they say that there are a lot of Gaussians in your data set, and you want to find the place where these Gaussians are farthest apart from each other. So in that case, you can, if you take any data point, you can report how far it is away from the center of the cluster that it belongs to. So that could be a measure of significance. If you have a point which belongs to a cluster, but then it is equally far away from many clusters, then you would say that the classification, that clustering mechanism of that data point is not very significant. But then what is this threshold? There's not very specific threshold that you can set in clustering. In the classification task, generally what you get is probabilities. You generally get a probability that most probably, or there is a probability associated with an object being a star or a galaxy or a jet or whatever we have seen. So these probabilities will let you form some form of a posterior, and from there you can maybe generate some form of significance. If it's like, let's say if it's a uniform distribution, it is not significant at all. So you just say your machine has failed. If there is a very big distribution, there's a very high probability of it belonging to a certain class, then you would say that, oh, there's a very high significance that it belongs to this class. But you can't give a number to the significance. That is something that depends on you. You set some threshold.
Yes.
Does that make sense?
Yes, sir. Yes, sir. Oh. Yes, sir. I got the difference. Yes, thank you.
Okay. Thank you. Okay, so Arpita's query has been clarified. See if there are more. So one person has asked, the IRIS data is around 5 GB. So yes, IRIS data is around 5 GB. It's very large. That's why I gave you Colab links. So Colab download doesn't use your internet. It uses the Google's internet, Google's host internet. So what you do is, if you still seeing my screen, click on this this arrow here, and click on connect to hosted runtime. Hosted runtime means you're not using your internet; you're using Google's servers. So they are only incurring costs for all of this download, not you. So don't worry if it's too large. If you're using Colab, it will download using the internet of your host, not you. Okay. So one person has asked about WCS. Okay, WCS is called World Coordinate System. This is from the previous lecture. And what we were doing in previous lecture was that the WCS is basically telling you what coordinate system something belongs to. So this coordinate system can be in space, in RA, deck and time, or in RA, deck and wavelength, if you're taking spectra of each object. So it depends on what you are observing and how you are observing and things like that. In the previous lecture, we had this thing called index. So this index basically is telling me what time step I'm supposed to take. So, and WCS also offers you, all of this, repository for doing the transformation from one coordinate system to the other. Let's say you want to go from RA deck to ALTAS. There is a prescribed way of going from RA deck to ALTAS using WCS. All of this is like some big table which is present, which is developed by AstroPy folks, and it basically uses these things. And how do they use? How do they know what coordinate system you are in? All of this information should be present in your FITS file. Every data file should have these information. I am looking at this object, at this array, this declination, the coordinate system spacing is so much, and so on and so forth. What is the rotation? So sometimes your telescope is rotated by some amount. So you should also mention how much it's rotated by with respect to which axis and things like that. So all of these information about coordinate system transformation, the coordinate systems themselves is present in a WCS. If you want to know more about WCS, go to AstroPi's website and click on WCS. It contains a very good repository of all the information. Okay, we are seeing our chat window as a black patch. Yes, you're supposed. I can't help it. It's supposed to not show anything. It sees the chat window as a black patch. And you can't see my chat window, I think, because that's against the security rights. So that's why I'm reading out the question and answering it. So some of you have asked for an extra lecture. So if you really want that, please talk to Dipanjan or one of the organizers. But what would you want me to do is something I don't know. Then you should let me know what you want me to do. Then maybe we can take it forward. So one thing which people have asked is this thing uploaded on the PBWorks website? Yes, it is on the PBWorks website. So this is the PBWorks front page. If you're still seeing my Firefox tab, this is the PBWorks website. You scroll down. You find my name. There's a page here, Python and Machine Learning Module. Click on that. And you find that, I have put up a lot of information here. The GitHub link is here. This GitHub link contains all the presentations, the notebooks. This day 2 presentation will go there after I add the references. And then this discussion section on GitHub is also present. So feel free to, put whatever questions you have on the GitHub, we can answer them. So that's, I guess, all the information that you folks need. So yeah, fine. If so, Abhijit wants some tutorial sessions. So please ask Dipanjan. What I can do is I can share these notebooks. I can share, I have a classification notebook. I can share that also with a lot of information. And if you keep getting questions, you can put those questions on the discussion in GitHub, and I can keep answering them. So yeah, you have afternoons. I have meetings in the afternoon, so it's not like I have afternoons free. So I would probably see them in the evening or maybe when I'm free. So any more questions? Any specific questions you might have? You can raise your hands or speak out. You can just ask in the chat, and I'm monitoring chat. And thank you, John. John clapped. It's very nice. Okay, so it doesn't seem like we have any more questions or doubts. So in that case, please go ahead and read more on this. I'll provide you some references on machine learning very soon. Please read those references. And if you think this all was very confusing, just take home those 3 exercises that we did of classification, regression, and clustering. Just those 3 exercises. That sort of summarizes what machine learning is in some level. So it's not just the exercises that you do, it's the reasoning you give. Why did you think there were 2 clusters? Why did you think, it's a galaxy? So that reasoning and why how did the data guide your reasoning? And how did the physics that or how the summer school or this apprenticeship course guide your reasoning? These things is what you will feed into a machine, teach it and use it for doing any inference you want. If you understand this much, then you have a very nice overview of what machine learning actually does. And you can actually go and read some papers or the Astro papers, which is machine learning. The details, when you want to get to the details on how each and every step is done, you can please go look at the notebooks which we have seen yesterday, and you just follow the procedure on how it's done. That's basically how everybody does machine learning. There's nothing more fancy than that. If you want to know why some things are done in certain way or why certain algorithms work in certain way, then you'll have to go ahead and read the references which I'll present soon. If you have any more questions, like the question on matplotlib, for example, please go and post your question in the discussion section in GitHub. Start a new thread if you want. Have a good, nice discussion. And if you already know some answers to these questions, please feel free to go ahead and answer them. There is absolutely no problem with that. So with that, I'll stop sharing, and I guess I am done now. Santosh, I think we can close now because we don't seem to have any more questions now. I don't know if Santosh is around. Santosh, are you around? Okay, let me send Santosh a message. Or maybe he's gone for lunch. It's lunchtime now. So okay, I guess I just close you can all leave. I'll just stop the recording, and then we can all leave and break for lunch. Okay, so